Let's talk about the rules of quantum mechanics. So first, a little background. Our quantons have different types of characteristics. Some of these are intrinsic, such as the mass and the charge, things that don't change. And some of them are what we call observables, things that change. For instance, their position, momentum, energy, and the one we've been discussing recently, the projection of a spin on a certain axis. The goal of quantum mechanics is to predict the results of experiments that measure these observables. And so the rules are going to give us a recipe for doing this. Now, just one note, these rules were built by a conglomerate of people, so it's not like Newton's laws where everyone agrees on them. They're all roughly the same, but everyone organizes them and numbers them a little bit different, so just be ready for that if you see the rules somewhere else. These rules, when we talk about them, we're going to break our systems into subsets. And these different subsets, the ones that we're going to use, basically they just talk about different sets of related observables. And later on we'll talk a lot about the one-dimensional subset, which is when you have some object that is only moving in one direction. And this will include things like the position and the momentum for your quanton. The one we're going to talk about now, which we've been talking about lately, is the spin subset. And these subsets are independent. And so generally you can focus on one while ignoring the others, like what we're going to do. We're going to talk about the spin subset because it is a very simple system that is really good for illustrating some of the interesting aspects of quantum mechanics. And we'll ignore the other ones while we're doing this. So the very first rule is there's a state vector. So the state of a quanton at some given time is given by a normalized state vector. This vector will have a certain number of complex components, and there are as many of these components as there are possible values for any one of the subset's basic observables. And so here the observable is the projection of the spin along some axis. All right, and we know that there's two possibilities, plus or minus h bar over 2. Basically your spin is up or down, aligned or anti-aligned with whatever axis you're talking about. So our special vector, and so this is where our complex vectors are going to be handy, will look like this. And this is a state vector. And so a lot of today is basically going through and talking about how this is going to help us predict the results of experiments and what this thing really means. I think getting your head around the state vector can take a little bit of time. But there's two components here, and so that's why we like to start with spin, because it's pretty simple. It's only a two-component vector. And just so your notes, these vectors are normalized. So if you take psi1 absolute square plus psi2 absolute square, it should equal 1. So the big question I get from students right away with the state vector is, what is a state vector? Like I said, I think it's difficult to get your head around this. A quantum state vector is a mathematical description of a quantum mechanical system. These vectors, these will be ket vectors, or abstract entities that obey many of the same rules we know about ordinary spatial vectors. So sometimes our knowledge of ordinary spatial vectors will be helpful. But because these vectors are abstract, it's hard to say much about them except how they behave mathematically and how they lead to physical predictions. All right, so we're going to learn recipes for how these vectors are going to help us predict the results of experiments. But the vector itself, as far as anyone knows, doesn't really represent anything. There is no physical representation of it. And a quantum state vector describes future possibilities but rarely determines anything. And so we're going to have this probabilistic part that we've been talking about. And so here's just two different ways that we'll represent these state vectors. So here's representing this as a combination of two kets, all right? And then these kets are always going to be, we can always write them as a column vector. And so you also have this version of writing it as a column vector. We'll sort of show you how this works as we go along. What's good, I think, is to go back and just think about classical systems. Now, we've done classical systems, and no one ever talked about the state of a classical system, but it is something you can talk about. And in classical physics, knowing the state of a system implies knowing everything necessary to predict the future of that system. All right, so for instance, in a projectile, if you have the initial position, the initial velocity, the acceleration, you can predict what's going to happen to that projectile. And so that's knowing the state of the system. Now, we don't even really talk about that because it's just, we do it so easily in classical. Unfortunately, in quantum physics, we're not going to have this luxury. All right, what we know about the system is the state vector, and this is all that we know, as far as we know at this point, about the system. And so it's going to be less. We're going to know less about our systems than we would classically. The second rule is the eigenvector rule, and this says for every possible numerical value that an observable might have, there is an associated normalized state vector, which we call that value's eigenvector. And that particular value is called the eigenvalue. All right, so for instance, we know in our experiments we can measure the spin along the z-axis. And so here is the eigenvector spin up for the z component of the spin vector. Here is spin down for the same measurement. And so here the eigenvectors are these two column vectors. The eigenvalue would be plus h bar over 2 or negative h bar over 2. Now we can also do this experiment, so this is the spin down for z component. We can also do this experiment, of course, along, say, the x direction and the y direction. We'll talk more about the y direction later, but today here are the two eigenvectors for the x direction. We'll talk more about where these come from, but now we're just sort of going to treat them as knowns and try to use them to do some different things. Now just one thing to note, a quantum state function can be an eigenvector. All right, and so you can, for instance, if you're measured spin up in the x direction, this will at that moment be your state vector. Now I like to draw little diagrams here just to kind of hopefully shed some light on some of this. So here's just a basic two-dimensional vector. We have our x and y unit vectors, right? And so then we have a and b being our x component and our y component for some, maybe it's a position vector, some vector that we may have used in first year. Now we'll find that these orthogonal unit vectors are very useful. Well, we're going to have the same thing in quantum mechanics, and I should really just stress that this is a cartoon. Okay, you can't really, sometimes when I draw these, people think there is some physical representation. This axis, and I made it kind of not exactly at 90 degrees to emphasize this a little bit, is just in our mind. It's not, it has no actual representation. But you can think about the positive x, okay, eigenvector, and the, positive z and negative z eigenvectors as spanning the space in the same way that the x and y unit vectors do. All right, and so we'll find that you can write any state vector regards to an object's spin, its projection of its spin, in terms of these two eigenvectors, where you would have, just like in the other case, you'd have the a and b being the component. So your component in the positive z and your component in the negative z. Now again, there is no relation to real space here, so you got to be careful with this analogy, but at least for me, I think it's helpful to think about it this way sometimes. So let's stop here and start working with some of these vectors. So here, what I want to do is, up here I have a state vector written right here in terms of two eigenvectors. Now we just learned these eigenvectors. Here they are over here. I want to express this state vector as a column vector. So maybe pause, go through and try this and see what you come up with, and we'll talk about it. Okay, so hopefully you had a chance to do this and you got E. So in order to do this, what you're really going to do is you just plug in the column vector straight into there. So we have 1 over radical 2, and so I'm going to put in the column vector 1 over radical 2 here, and 1 over radical 2 there, and then plus 1 over radical 2, and so the only difference here is that it's 1 over radical 2 and then negative 1 over radical 2. And so I'm going to multiply this 1 over radical 2 inside of there, and I just get 1/2 plus 1/2 negative 1/2. So this one works out pretty nicely. You get 1 and 0, just as we said. So it's always just doing that to basically convert from this form to a column vector. And a column vector can usually be a little bit easier because you're doing a lot of multiplication of these vectors, and so it's usually easier to treat it as a column vector when doing that. The next rule is probably the most controversial, and it basically just says, this is the collapse rule, that when we perform any experiment to determine the value of one of our observables, the experiment determines the observable's value by collapsing the quantum state to a randomly selected one of that observable's eigenvectors and yields the eigenvalue corresponding to that eigenvector. All right, so suppose this is our state vector. So the psi1 and psi2 are both non-zero. And suppose then we take this and we try to measure the projection of the spin in the z direction. So we try to measure sz. Well, the state vector, when we measure, will collapse to one of the sz eigenvectors. Now, as long as both of these are non-zero, we don't know which one. It'll be either A or B. Okay, but our state will change, and so this is a change in our state. If our state was this beforehand, it'll end up now being in one of these eigenvector states, which means we'll end up having the eigenvector corresponding to that particular one. So this would be, spin up, so h bar over 2 for this one, and then negative h bar over 2 for that one would be our eigenvalue. And so, again, as long as that psi 1 and psi 2 are non-zero, there's going to be a chance that either one of those could happen. Just then to explain some terminology here, because it can be tricky. So we have sort of three things that I think are easy to mix up. We have the observable, the eigenvalue, and the eigenvectors. The observable is what we're measuring, and so here it's the projection of the spin along some axis. So we've sort of talked a little bit about the z and the x, and we'll talk about y later. The eigenvalue is the actual value you get. So if you measure the spin on the z-axis, you get either plus or minus h bar over 2. And the eigenvector is the new state vector that you'll be in after that measurement. And so here you'll be in the positive or negative z if you go through a z machine. If you go through a SGX, you'll end up either being positive or negative x, and of course the same thing for y. Now, in general, your state vector, okay, can be some combination of these, and some linear combination. So here's some combination of being positive z and negative z. Now, what that means, again, gets into this realm of interpretations of quantum mechanics. Okay, but we'll talk more about this. The outcome probability rule is the way that we can figure out the probability of something happening. And basically it works like this. In order to find the probability of some measurement, you take an inner product. Okay, again, we talked about this, how these inner products are a bracket, right? And so the way that it works is this is your initial, and then this will end up being the measured, or final might even be a nice way to put it too. And so with this inner product, okay, this inner products, we're going to call these inner products quantum amplitudes. Quantum amplitudes. And the way that it works is this is your initial, this is your final, and so we're going to take this and we're going to then square it, take the absolute square, and so this is the probability that an electron in this state psi that goes through an SZ Stern-Gerlach device will exit from the positive channel. So this thing right here ends up being that probability. And of course you could do this for the negative z to find the other probability. And so there'll be lots of questions where you're asked the probability, and you're always going to want to find an inner product and then take its absolute square. And so if you look at this, it can kind of help understand some of these experiments you've done before, at least mathematically. So first of all, if I take the inner product of positive z and positive z, and I square that, I get 1. And that's just saying that this experiment here that we talked about last time, that's how you would sort of calculate it. And so I take the electrons coming out of the positive side of this z machine, which means they're all in the positive z, and I calculate, all right, what's the chances of them ending up in positive z, and it turns up to be 100%. All right, so that's self-consistent with itself. But also from this, we can find that you can calculate here, this is 0. Okay, so the chances that if I start out in the negative z and end up in the positive z is 0, because these two vectors will be orthogonal. All right, and so you can always do this calculation here to go through and find probabilities for different experiments. And so let's try one. So here's the next one. So suppose an electron is in the state psi before. What is the probability that this electron will exit from the positive channel if it is sent through an SGZ device? So give this a try, and we'll talk about it in a little bit. So for this one here, I got 1/10, and again, what we want to calculate here is we want to calculate an inner product. And so we're trying to find which likelihood it'll come out from the positive channel of SGZ. So I want to take positive Z with my psi before. And so the positive z is just 1, 0, like so. And then this one is 1 over root 10, 3 over root 10. And so when I take this inner product, I get a scalar, which is 1 over root 10. And now the final step is I want to take that and take the absolute square. So that's something that sometimes people can forget, so you got to be real careful. So I'm going to take the absolute square of this, which is just 1 over root 10, and so I get 1/10. So 10% chance that it's going to come out from the positive end of the SGZ device. All right, rule 5 is the sequence rule. And so this says if a quanton is initially prepared in some state size 0, and we determine the value of observable A to be AN, and then immediately determine the value of observable B, the quantum amplitude of some particular result B1 is this. Okay, and it's basically two inner products multiplied by each other. All right, and so this is the quantum amplitude of basically two measurements coming after each other. All right, and so the way this works, if you look at this, there's the initial state there, which is the ket, and then you end up in a bra of the final state, and then that's your second measurement. And so this is the first measurement, AN, in there too, and then the other AN. And so basically there's four little entries. These two here will always be the same, right? And so when you do this. So another way to kind of think about this is it's two quantum amplitudes. And so this is the quantum amplitude here to be measured AN if you're in the state psi sub 0, and this is the quantum amplitude to be measured B1 if you're in the state AN. And so it's sort of like here's the probability of me being measured to be in AN, and then once I'm in AN, here's the probability of me being measured to be in B1. And you multiply these two things together. We're going to use this a lot as we go forward. And the last rule we'll talk about today is the superposition rule. Consider an experiment where a quanton can take either one or two paths from its initial preparation to some final observation. And we can't know which path the quanton took, so we've done a lot of examples of this, and now we're going to look at this mathematically. The total quantum amplitude for the final result is then the sum of the amplitudes for each possible path. And so it's really important. So if there's two different paths to get to some final observation, then the quantum amplitude is the sum of each individual amplitude. And so for an example, let's look at this here. So there's a sequence of SG devices. There's an SGZ, an SGX, and then an SGZ. All right, and I want to know is what's the quantum amplitude to exit over here at the blue arrow. And there's two paths. All right, so what's happening is we have these SGZs, and so we collect the positive SGZs, and then there's two paths. There's the top path and then the bottom path. So go ahead and pause and think about this, and we'll talk about it in a little bit. All right, so now this is tricky, and I got this here to be my answer. So again, what we're doing is there's amplitudes to go through the top path and the bottom path, and then the thing is if we don't know which path it took, then to find the total amplitude, we just add them up. And if you look, say, for instance, at this one here. So this one, I'm starting at positive Z. So again, over here, I start at positive Z, and I'm measured to be negative Z. So this is if I'm taking the bottom path. All right, and so this is the probability of that, and this is the probability if I'm in that negative Z that I actually get measured to be, if I'm in that negative X, I get measured to be negative Z. This is the other path, okay, the amplitude for the other path. And so here again, I start positive Z, and here my intermediate is positive X. And then still, it ends up being whether or not I'm in the negative Z. All right, and then we add these two together for the total quantum amplitude. And this is going to help us explain this last experiment from last time that was confusing to a lot of us. And so in the one case, if I block off the bottom path here, what I'm doing is I'm collapsing the state function. So I'm basically forcing the particles coming into the final SG Z device to be positive X. And if they're positive X, it's very easy to calculate. Well, if you do that, half will be spin up, half will be spin down if they go through the Z machine. Right? Now the other thing is that with the really kind of crazy part is this idea where we have the two paths. Right? So we have the top path and the bottom path, and we combine them. Right? What happens is it's just like this middle machine wasn't here, and they all come out 100% over here. And so now we have a way to calculate this. And so this is the amplitude we just calculated in that clicker question. And again, this is the amplitude to come out negative Z. And so here I've put in the different column vectors, and I definitely urge you to go through this to make sure you agree with everything. And so you're basically calculating a total of 4 inner products here. And so here I got 0, 1 times this, and so this will just be 1 over radical 2. And this one here, the same thing, 1 over radical 2. And I'm saying plus, and now here, this is sort of the key. This 1 times this gives me a negative 1 over root 2 for this inner product here, and then this inner product will come out to be 1 over root 2. And so this whole thing comes out to be 1/2 minus 1/2, or 0. And so then if I was to take the absolute square here, I get 0, which is of course what we find. Okay, so these really weird experiments, this is how we can use the rules of quantum mechanics to at least figure out the results.